Hello, Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today's question has to do with understanding the standing wave ratio in terms of the reflection coefficient and vice versa. As it turns out, SWR is a measure of the amount of energy that is reflected by something, the antenna, usually in our case, back into the device where things start. Let's take a look at that on the whiteboard. Now, the reflection coefficient is often written as capital gamma. Okay, this is a Greek letter. It's the capital of gamma. I know it looks weird. You're wanting to put in that part to the F. This consists of a magnitude and phase angle. I want to talk a little bit about magnitude. If you've got the complex plane here, where this is I, and this is minus I, and this is 1, and this is minus 1. Okay, this is the complex plane. If you take a point out here, the magnitude, or absolute value, the magnitude is the length of that line. Now, I know we're used to, when we talk about mathematics, that absolute value means just drop the minus sign. Now, it's a little more complicated than that. The magnitude is how big this thing is here. Now, if we take the absolute value of this, all we are looking at is the magnitude, and the phase angle goes away. Okay, so that's why you will see it in these terms. Now, if we look at an antenna, we've got a radio, or I'll just call it a transmitter, and it puts out a signal to the antenna. You've got the forward signal and the reverse. So you send this up, it sends a little bit back. Now, where does it go? In the transmitter, it goes into the final amplifier and heats it up. Okay, so there are limits on the amount or the size of the reflected power. Now, the reflection coefficient is the ratio of these two. So you take the reverse over the forward, and you've got to remember, we're dealing with RF, so we need to keep our phases straight. So absolute value of that is the reflection coefficient, gamma, or in this case with that. Now, knowing that, we can directly calculate SWR. The absolute value of the reflection coefficient, which is the part that we're usually interested in, we don't care about the phase, and in this case it really is irrelevant. It's equal to the standing wave ratio minus 1 over the standing wave ratio plus 1. So let's take some examples here. Let's suppose SWR is 3 to 1, okay? So that would make this part right here, the top part, it would be SWR minus 1 is 2, and over SWR plus 1 is 4, or 1/2. So the reflection coefficient is half. That means half of the power is reflected. So if you send 100 watts this way, you get 50 back. Now this is about the max that you can tune with most radios today. And that's obviously a lot of power. Now, let's take another example and suppose that the ratio is SWR equals 1.6 to 1. So it would be SWR minus 1 is 0.6 divided by the SWR plus 1, which is 2.6. If we get out our handy calculator, we see that 0.6 divided by 2.6 is a quarter. So in this terms here, we're getting now a reflection coefficient of 0.2. 2, 3. Okay. This is a great deal less power. Okay. Now, while we're sitting here, it'd be so easy to understand how antenna tuners work. Remember, I said that if you have a transmitter and you've got an antenna, and let's suppose the antenna and feed line combined has a 1.621 SWR, we have a tuner. In this, we send 100 watts this way, 100 watts this way, 25 come back. Now, if the tuner is set to the complex conjugate, and now we're talking including the phase of this, the tuner will catch that, and on the next wave going through, we'll add it back, and so it will go up here to have another chance at radiating. Some of it will be reflected back, and you go through this thing until finally it's imperceptible. Now, if you have a 1.6 to 1, you're not dealing with huge amounts of energy here, power lost in the line. It's the current that matters and the resistance. The wire resistance here is 50 ohms because we're dealing with RF here with 50 ohms. Okay, so it goes up as the square of the current, which is why we want to keep the SWR low. If this is a real high SWR, then that current makes many ping pongs back and forth here, and it's being refreshed every time, and we end up with a lot more current in the wire, and that is just simply radiated away as heat in there. So that's why if we have a high SWR, we like to use ladder line because of the way this thing works. You get the R in there higher, turns out you lose less power. Okay, and you can play with the equations if you would like to. So what we have learned is that there's lots of things you can do with Ohm's law, the power law. Remember, Ohm's law equals IR. The power law, power equals E times I times the sine of the phase angle. Other laws for the SWR, if you look at the actual waveforms in there, one's this high, one's this high, you divide them, you get the SWR. You can also compute SWR from the power factor, and you can compute the power factor from SWR. It all comes in together. These are interesting to play around with, not necessarily because they're going to be crucial to you getting a station that works, but to give you a better understanding of what's really going on inside your cable and antenna. There you have it. We've talked about a very simple way of looking at SWR and the reflection coefficient and the proper mathematical way to combine the two. So, until we next meet, 73.